Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclair.
Welcome to Teolumen Insights. Ever thought, about what it'd be like if, the rules of Einstein's relativity, apply to something as basic as sound? That's what we're diving into today.
Yeah.
This wild concept of sonic relativity.
Most people think of sound and light as completely separate things, but what if we could create a universe where sound behaved more like light? That's what physicist Nick Menicucci has done with his work on sonic relativity.
So we're basically creating a mini universe where sound is king.
Right.
The fastest thing around.
Yeah.
But how does that actually work? I mean, sound is just vibrations, right?
Right. But the key here is shifting our perspective on how we measure space and time.
Okay.
Imagine a world where beings, let's call them sonic observers, can only experience the world through sound.
Interesting.
It'd be like a world of superpowered bats using echolocation to understand everything.
So instead of using light to measure time and distance, these sonic observers would rely entirely on sound.
Yes.
That's crazy.
Exactly. And that's where things get really interesting.
Yeah. Okay.
Because by using sound-based clocks and rulers, these sonic observers would actually experience relativistic effects.
Interesting.
Like time dilation and length contraction, just like in Einstein's theory.
Wait a minute. So you're telling me that just by changing how we measure things, we can make sound act like it's bending the fabric of space and time?
Yes.
That's blowing my mind a little.
It is pretty wild. And what's even more fascinating is that the underlying physics at play in this sonic universe is still good old Newtonian mechanics. It's just that the perceived reality for our sonic observers is governed by relativistic principles.
So it's all about perception.
Yeah.
Their reality is literally shaped by the limitations of how they measure things.
That's the beauty of it. It makes you question what's truly fundamental and what's simply a consequence of our measurement tools.
Right.
And it all starts with how these sonic observers construct their unique tools.
Okay, I'm hooked. Let's talk sound clocks and rulers.
Sure.
How do they actually work?
Imagine our bat friend sending out a sound pulse, having it bounce off a surface, and then measuring the time it takes to return.
Yeah.
That's their version of a clock.
Makes sense.
And for a ruler,
they'd
send out two pulses simultaneously and measure the distance between the return points.
Simple, yet elegant. But how does that lead to time dilation and length contraction? It still feels like there's some magic going on here.
No magic, just physics. Let's say our bat is flying through the air. Even though they can't directly perceive their motion relative to the air, it affects their measurements. For a moving sound clock, the sound pulses have to travel a greater distance. So the clock ticks slower compared to a stationary one.
Ah, I see.
Yeah.
And for the ruler, the return points would have to be closer together to account for the bat's movement.
Exactly.
It's like the ruler's shrinking.
Exactly.
Yeah.
And that's the essence of length contraction in this sonic world. These relativistic effects emerge not from some inherent property of space and time, but from the limitations of how our sonic observers measure those quantities.
Okay, that's mind-blowing.
Yeah.
But here's a question.
Okay.
What happens if our sonic bat encounters something that doesn't play by the rules of their sonic universe? Like a tiny speck of dust.
Okay.
Just a normal particle that doesn't care about the sonic speed limit.
That's where things get even more interesting.
Okay.
To our sonic observer, this dust particle would behave in completely unexpected ways. If they tried to bounce a sound wave off it, the results wouldn't make sense according to their sonic laws of physics.
So it'd be like their whole understanding of the universe was suddenly thrown into question. That's got to be a rough day for a bat.
It would be a huge challenge to their worldview. Yeah. They might even try to come up with new theories, proposing a different kind of medium for these strange particles to travel through, even though we know in our universe that's not the case.
So they'd essentially reinvent the ether theory.
Yes.
Which we abandoned ages ago.
Right.
But wouldn't that allow them to detect their own motion through the sonic medium?
Yes, it would.
Something they couldn't do before.
But what's even more fascinating is that there's another more relativistic explanation available to them. It involves this wild concept called a tachyonic medium. a kind of ether for particles that always travel faster than their sonic speed limit.
Hold on, tachyons.
Yes!
Those are particles that supposedly travel backwards in time, right?
You're right.
Wouldn't that create all sorts of paradoxes?
But remember, our sonic observers are limited by their sound-based perception.
Right.
They wouldn't be able to observe true causality violations, even if these particles were behaving like tachyons in their world.
Okay, my head is officially spinning.
Yeah.
How do they square this idea of superluminal particles with their sonic relativity without breaking the laws of physics?
It all comes down to how they perceive this tachyonic medium. Instead of seeing it as an absolute reference frame, they would perceive it as having its own rest frame, just like their sonic medium. This neat trick allows them to avoid the paradoxes associated with faster-than-light travel.
Wow, this is getting deep.
It is.
So they basically have a separate set of rules for these superluminal particles, almost like a hidden layer of reality that only these special particles can access.
Exactly.
Right.
And that's a key takeaway here. Our perception of reality is shaped by the tools we use to measure it.
Interesting.
Just like our sonic observers, we might be missing aspects of the universe. Simply because we haven't figured out the right way to observe them.
This is incredible.
It is.
So by taking sonic relativity seriously, we're not just playing a fun thought experiment.
Right.
We're actually questioning our own assumptions about what's fundamental in the universe and what might be a consequence of our limited perspective.
Absolutely. It's a powerful reminder that there's always more to discover.
Right.
More layers to peel back. And that the universe is full of surprises waiting to be uncovered.
I'm already eager to dive deeper into this sonic rabbit hole.
Me too.
But before we do, let's take a moment to reflect on what we've learned so far.
Okay.
We've seen how sonic observers using sound-based tools can experience relativistic effects.
Yes.
Even though their underlying reality is based on Newtonian physics.
And we've started to grapple with the mind-boggling implications of tachyonic mediums and the potential for hidden layers of reality that lie beyond our current understanding.
This is truly mind-expanding stuff. But before we get too carried away, I think we need a moment to catch our breath and process everything. We'll be right back after a quick break to delve further into the fascinating world of sonic relativity right here on Teolumen Insights.
Looking forward to it. So before the break, we were talking about how our sonic observers might interpret, those particles that don't obey the sonic speed limit.
Right, those Newtonian particles.
Right, exactly.
Yeah.
Now, I want to shift gears a bit and introduce this concept of an inertial observer.
Okay, an inertial observer sounds kind of like a Star Wars character. What exactly does that mean in the context of sonic relativity?
Well, in both standard relativity and sonic relativity, an inertial observer is simply an observer that's not accelerating. They're moving at a constant speed, either through the fabric of space-time or through a medium like air or water, in the case of our sonic observers.
Got it. So our bat friend just cruising through the air at a steady speed would be an inertial observer.
Right, exactly.
Sure.
Now, the question is, how do the measurements taken by two different inertial observers relate to each other, especially if they're moving at different speeds?
I'm guessing their measurements of time and distance would be different, right?
Yeah.
Since we already know that motion affects how our sonic observers perceive those things.
You're absolutely right. And the tool we use to connect these different measurements is called the Lorentz transformation. It's a mathematical equation that allows us to translate between the space and time coordinates measured by two different inertial observers.
Okay, I vaguely remember Lorentz transformations from like my physics classes.
Yeah.
But those were always in the context of light and the speed of light being constant.
Right.
How does that apply to our sound-based universe?
It's actually very similar. Instead of the speed of light, we use the speed of sound as our constant.
Yep.
So if we have two of our sonic bats moving relative to each other, we can use the Lorentz transformation to figure out how their measurements of time and distance will differ.
So even though these sonic observers live in a world governed by Newtonian physics, their measurements will still exhibit those relativistic effects.
Exactly.
Like time dilation and length contraction, just as if they were dealing with the speed of light.
Precisely.
That's amazing.
And this is where we can introduce the sonic equivalent of the gamma factor from Einstein's theory.
Okay.
It's called the sonic gamma factor. And it tells us how much time dilation and length contraction occur based on an object's speed relative to the speed of sound.
So the faster our bat is flying, the greater the time dilation and length contraction it experiences.
Exactly. And the formula for the sonic gamma factor is almost identical to the one in special relativity.
Okay.
The only difference is that we replace the speed of light with the speed of sound.
Okay, I'm seeing how the math from Einstein's theory can be applied to this sonic world.
Yeah.
But let's go back to those Newtonian particles that don't obey the sonic speed limit.
Yeah.
How would our sonic observers make sense of their behavior?
That's where things get a bit more complicated. Remember we talked about how they might interpret these particles as traveling through a different kind of medium,
Right.
a tachyonic medium.
Right.
To accommodate this, they'd need to adjust their understanding of how energy and momentum are related for these particles.
Right, because in their world, energy and momentum are still connected.
Yeah.
But the relationship is based on the speed of sound, not the speed of light.
And this relationship between energy and momentum is described by what we call the relativistic dispersion relation.
Okay.
It basically tells us how a particle's energy changes as its momentum increases. Don't worry, it's not as scary as it sounds.
Okay.
The basic idea is that for particles that obey the sonic speed limit,
Right.
their dispersion relation would look very much like that of photons in our universe. The only difference is that we'd swap the speed of light with the speed of sound.
Okay, so far so good.
Yes.
But what about those Newtonian particles that break the sonic speed limit?
For those, our sonic observers would have to come up with a different kind of dispersion relation.
What?
They would need one that can account for their superluminal speeds.
Right.
And one way to do this is by introducing the concept of tachyonic mass.
Hold on, tachyonic mass. Now that sounds like something straight out of science fiction. What does that even mean?
It's basically a mathematical trick that helps us describe particles that always travel faster than sound. It's a way of incorporating those superluminal speeds into their existing framework of sonic relativity.
So they would essentially have two sets of rules.
Right.
One for particles that obey the sonic speed limit, and another for those that don't.
Yeah.
Wouldn't that create a sort of duality in their understanding of the universe?
It would. And that's exactly why the behavior of those Newtonian particles would be so perplexing to them. It would force them to grapple with some very fundamental questions about the nature of reality.
This is really fascinating. I can see how this thought experiment with sonic relativity can help us understand the deeper implications of Einstein's theories in a more intuitive way.
Exactly. It's a great way to explore those concepts in a more accessible way without getting too bogged down in the complexities of general relativity.
Speaking of complexities, you mentioned something earlier called acoustic black holes.
Yes.
What are those?
Okay.
And how do they fit into all of this?
Right. Acoustic black holes are another amazing example of how sonic relativity can be used to model and understand complex phenomena.
Okay.
Basically, an acoustic black hole is a region in a fluid flow where the speed of the flow exceeds the speed of sound.
So like a sonic boom in reverse.
In a way, yes.
Okay.
Just like nothing can escape the gravitational pull of a black hole once it crosses the event horizon. Sound waves can't escape an acoustic black hole once they're trapped within this region of supersonic flow.
Wow, that's incredible. But why are these acoustic black holes important?
Because they offer a unique opportunity to study the behavior of light and matter.
Okay.
Near real black holes, but in a controlled laboratory setting, we can actually create acoustic black holes in the lab and observe how sound waves behave around them.
So it's like a miniature model of a real black hole, but using sound instead of light.
Exactly. And by studying these sonic analogs, we can potentially gain insights into some of the most mind-boggling predictions of general relativity and quantum field theory, like Hawking radiation, which suggests that black holes aren't entirely black, but slowly leak energy and eventually evaporate.
Hawking radiation.
Yeah.
That sounds pretty intense.
It is.
So we might be able to observe this phenomenon in a lab.
Potentially, yes.
Using these acoustic black holes.
While we haven't directly observed Hawking radiation from real black holes, there's growing evidence that it can be detected in these sonic analogs.
That's amazing. So we've gone from sound waves and bad echolocation to modeling black holes in the lab.
Yeah.
The sonic relativity thing is really taking us on a wild ride.
It is, isn't it? And it all stems from the simple idea that sound, just like light, can be used to explore the fundamental nature of space-time and gravity.
This has been such an eye-opening conversation.
Yeah, me too.
We've covered Lorentz transformations, sonic gamma factors, relativistic dispersion relations, and even acoustic black holes, all within this framework of sonic relativity.
And we've only just scratched the surface.
I know, right? It's amazing how this simple concept of sound waves can lead us to such profound insights about the universe.
It is.
Before we get lost in the math and physics, though,
Yeah.
I think we should take a moment to discuss the bigger philosophical implications of what we've learned.
Okay.
What does sonic relativity tell us about how we construct our own reality? What are the limitations of our perception? And what might we be missing?
Those are some excellent questions, and I think they're at the heart of what makes sonic relativity so fascinating. It's not just about the equations, it's about what those equations tell us about the nature of observation measurement and the very fabric of reality. We can dive deeper into those big questions next time on Teolumen Insights.
So, welcome back to Teolumen Insights. Before the break, we were exploring some pretty heady concepts.
Yeah.
Lorentz transformations, sonic gamma factors,
Yeah.
even those mind-bending acoustic black holes.
Right.
But now I want to shift gears a bit and talk about what all of this means, on a bigger level.
Yeah.
What does this sonic thought experiment tell us about how we as humans construct our own reality?
That's a question that has been pondered by philosophers and scientists for centuries.
Right.
And I think what sonic relativity offers is a fresh perspective on the role of observation and measurement in shaping our understanding of the universe.
So it's not just about crunching the numbers and the equations.
Exactly.
It's about understanding how those numbers and equations reflect our own experience of the world.
Exactly. Remember our sonic observers, those bats navigating the world through sound?
Yeah.
They're completely unaware of the Newtonian mechanics that underpin their universe.
Right.
Their entire reality is built upon their limited sonic measurements.
Which, if I remember correctly, leads them to some pretty wild conclusions.
Yes.
Like the existence of a tachyonic medium to explain those Newtonian particles that don't follow their sonic rules.
That's right. And this highlights a crucial point. What we perceive as a fundamental law of nature might simply be an artifact of the tools we have available to us.
So it's like that old saying, if all you have is a hammer, everything looks like a nail.
Right.
If we only interact with the universe through sound, then everything will appear to obey the laws of sonic relativity.
Right.
Even if there's a deeper reality underneath.
Precisely.
Yeah.
And this raises a very interesting question.
Yep.
What aspects of our reality, the things we take for granted as fundamental laws of physics, might simply be consequences of our limited light-based perspective?
Whoa.
Right. That's a big thought.
Yeah.
Are you saying that we might be missing out on entire layers of reality simply because we haven't figured out the right way to observe them? There's a whole universe out there that we're blind to.
It's certainly a possibility.
Yeah.
And I think it's a humbling thought.
It is.
It encourages us to stay curious, to question our assumptions, and to always be open to new ways of seeing the universe.
It reminds me of how Einstein's theory of relativity revolutionized our understanding of space and time.
Mm-hmm.
It wasn't that Newton was wrong.
It's just that his framework was limited to a certain range of experiences.
Yeah.
Einstein came along and showed us that even seemingly absolute concepts like space and time are actually relative.
That's a great analogy. Einstein's genius was in recognizing the limitations of the prevailing worldview and daring to challenge it.
Yeah.
And in a similar way, sonic relativity challenges us to consider that even our relativistic understanding of the universe might be an emergent property of a deeper, more fundamental reality.
Like the universe is a giant onion and we're just peeling back the layers one by one with each new scientific discovery.
Right.
And who knows what we'll find at the center.
It's a mystery that's worth exploring. And the beauty of science is that it provides us with the tools and methods to continue that exploration, to keep asking questions and pushing the boundaries of what we know.
Well said. I think we've covered an incredible amount of ground in this deep dive.
We have.
We started with a simple question. Can sound exhibit relativistic effects? And ended up discussing the very nature of reality itself.
It's been a fascinating journey.
It has.
And I hope our listeners have enjoyed it as much as we have.
If you're eager to learn more about sonic relativity, be sure to check out the show notes for links to Nick Menicucci's work and other resources. And remember, the universe is a vast and mysterious place full of wonder and possibility. Never stop exploring, never stop questioning, and never lose your sense of awe. Thanks for joining us on this deep dive into sonic relativity. Until next time, keep exploring the frontiers of knowledge with us here at Teolumen Insights.